Hello everyone, welcome to WCCM2022. This is Han from CPRG, Computational Physics Research Group, National Taipei University of Technology, Taiwan. Today I'm delighted to report a numerical study of racing motorbike aerodynamic wing kit configuration using OpenFOAM CFD. Here is the outline today. We will share several cases. Due to the characteristic of a two-wheeler, the front wheel of a motorbike lifts when it accelerates to a higher speed. Therefore, downforce is necessary to maintain high speeds and forces a racing motorbike to the racetrack by keeping the front wheel on the ground. To obtain higher downforce, the absolute value of lift-to-drag ratio of aerodynamic parts should be as high as possible. This study aims to figure out the highest absolute value of lift-to-drag ratio of aerodynamic wing kit configuration through various angles of attack and wind speed. Initially, we used Java foil as the benchmark to prove the usability of the CFD toolbox OpenFOAM. Then we studied the grid independency to confirm the mesh quality. In case 1, we compared two riding positions of riders and applied the one with lower drag as the basic geometry. Case 2 studies the single wing. In case 3 and case 4, we study non-parallel wings and parallel wings. Based on the highest absolute value of lift-to-drag ratio of aerodynamic wing kit above. In case 5, we study the closed wing and run simulations of the LES model to analyze the vortex structure. Let's start with the motivation. Aerodynamic technologies have been a part of the winning strategy of racing teams for over 100 years. In the past decades, CFD is a valuable testing method to increase performance improvement efficiency and decrease the cost. The distinguished motorbike manufacturer Ducati revealed the aerodynamic wing kit in abbreviation AWK, on a MotoGP level racing motorbike in 2016. Since then, racing motorbikes using AWK has become a trend. However, the implementation of these kits is still like the secret weapons of top-end manufacturers. Relative research in this domain that providing specific numerical support of the association between wing kits installation and the downforce improvement is still insufficient. To understand the critical factor of wing kits' aerodynamic performance, a CFD study became necessary. Problem description. The overall study aims to figure out the highest absolute value of lift-to-drag ratio of aerodynamic wing kit, which means the highest downforce to drag ratio. Refer to the condition of racing. The inlet velocity of x direction was set to simulate the wind speed of 20 meters per second, 60 meters per second, and 100 meters per second. The geometry of 3D CAD models installed AWK using an ARCA 4412 airfoil with a self-defined center of rotation. The configuration keeps wings detaching from the ground by the lean angle of 70 degrees. The simulations of various AOA start with 0 degrees to minus 51 degrees and obtain drag coefficient and lift coefficient. Here is a computational domain with 35 meters in length, 10 meters in width, and 15 meters in height. We put the racing motorbike geometry in the domain, using the boundary condition no slip as the right-hand side. The inlet velocity starts with 20 meters per second, and the outlet pressure is 1 atm. The rest was using zero gradient. Notice the lower wall sets in zero gradient instead of no slip to simulate the moving ground. There are several 3D CAD models we've put into the computational domain. Case 0 is a partial fairing for a grid-independent study. Case 1, we use a racing motorbike as the benchmark. Compared to riding positions, choose the one with a lower drag in the rest studies. In case 2, we tested a single wing. The highest absolute value of lift-to-drag ratio occurs at -37 degrees. We used it as an upper wing in case 3 and rotate the lower wing. In case 4, we rotate both wings parallelly. The highest absolute value of lift-to-drag ratio in both case 3 and case 4 occurs at -41 degrees. So we modify the model of -41 degrees to a closed wing version and study the vortex structure. To improve the efficiency of the study, we were using Intel Xeon clusters. We run the case 2 single wing using parallel computing. The time step starts with 0 and stops at n times 500, with the right interval 100. For a better comparison, the delta t sets in 0.1 and eventually generated approximately 700,000 cells. The convergence criterion is 1.0 exponential -6. Started with one core as 100% efficiency. Once the cores increased, the speed got higher but the overall efficiency got lower. The comparison of efficiency and the cores is as the table. It's very interesting here we could see the superlinear speedup happens at 4 cores. With the results above, cases run parallel computing using Intel Xeon Gold 5218 with 320 GB memory. Governing equations. We use Reynolds averaged Navier-Stokes equations, in abbreviation RANS, in this study. It contains a continuity equation and momentum equations. To solve Reynolds trace, we use k-omega shear trace transport turbulence model. Based on the characteristic of the near wall function, in the viscous sublayer, use k-omega equation. In the turbulent boundary layer, use k-epsilon equation. We have to make sure the y plus value in each case must be under 5, and the lower the better. All the refinement level settings must follow this rule as well, even if y plus value increased with higher inlet velocity. Large AD simulation, in abbreviation LES. The converged results such as drag coefficient and the lift coefficient of the INS turbulence model are applied as the initial gas value using numerical analysis method to initialize the LES turbulence model solving. In this model, the large-scale components of the flow field are filtered from the small-scale components using a wavelength criteria related to the size of the ADs. In the schematic diagram, in the beginning we set up the boundary condition. The study is basically on the 0.3 Mach. To solve the incompressible flow problem, we choose the simple algorithm. For higher efficiency of converged results, the k-omega SST turbulence model is applied. The converged results contains velocity in x, y, and z directions, and the pressure in each cell. Through the Prost processing, we could get the lift coefficient and the drag coefficient. Then, in each case, we could obtain the lift-to-drag ratio. Here is a result of the benchmark validation. We use Java foil to obtain specific parameters such as lift coefficient and drag coefficient of NACA 4412 airfoil. Then, we run simulation using OpenFORM under the same conditions. The simulation result of OpenFORM, which the blue line approximately overlaid on the red line, generated by Java foil. It proved the usability of OpenFORM. Great independent study. We use snappy hex mesh to generate meshes. On the left-hand side, we can see in a higher refinement level that both cells and skewness increased. The usable skewness in open form should be under 20, otherwise the case may not converge. On the right-hand side, the picture shows a typical result of using snappy hex mesh. Unstructured meshes connected structured meshes. We created an extracted line behind the wing of the partial fairing to visualize the pressure contour in the z direction. The green line, which is the refinement level 5 to 7, generated 227 cells approximately, overlaid on the blue line, which is refinement level 5 to 8. The setting of the refinement level 5 to 7 passed the grid-independent study and it's usable. In case 1, the writing position study makes a comparison of two writing positions and creating 3D CAD model geometries to find the one which has a lower drag coefficient. As you can see, the right one, the dummy 2, has a lower writing position and a lower drag coefficient, which is applied in the rest cases. In case 2, the angle of attack from 0 to minus 51 degrees, the highest absolute value of lift-to-drag ratio appears at minus 37 degrees. Notice that while the inlet velocity increased from 20 to 100 meters per second, the y plus value got higher, but it's always under 5. In case 3, the upper wing is fixed at minus 37 degrees and rotate the lower wing. The highest absolute value of lift-to-drag ratio appears at minus 41 degrees. In case 4, rotate both upper wing and lower wing. The highest absolute value of lift-to-drag ratio also appears at minus 41 degrees. In case 5, rebuild the 3D CAD model into a closed wing version using parallel wings of minus 41 degrees. To increase the accuracy of the LES turbulence model, we choose a higher refinement level of mesh. The figure shows the quality of the mesh before and after around the AWK. Notice the skewness must under 20 and Y plus must under 1 while using LES model. The table shows a comparison of INS model and LES model. Notice the right-hand side, Y plus value. While the refinement level increased, the Y plus value decreased. It brings us higher accuracy of the converged results. With the appropriate facilities here in CPRG, we could create a case using 0.16 billion cells. We could even use a streamline tool with arrow-shaped patterns to make a comparison of the windless and the closed wing conditions. The airflow with a lower velocity, that blue part, stick around the back of a rider dummy. Here is a comparison of pressure coefficient contour between windless and closed wing conditions. The inlet velocity is 100 meters per second. This is another comparison of x-direction velocity. The contour number 1 and the contour number 2. We could see the difference between the windless CAD model and the closed wing CAD model with the inlet velocity of 20 meters per second using Q criterion isosurface. Once the inlet velocity increased to 100 meters per second, contour number 6 appears a huge vortex around the AWK, and contour number 5 doesn't. With the side view of the previous page, the vortex around the AWK became more obvious. The contour shows the velocity of x direction overlaid on the isosurface, while the Q criterion is 1000. In this video, we could see how vortex structure is generated and the progress of its dissipate. If we switch the camera to this angle and slow down a little bit, it's more clear how the vortex generated. With the contours of pressure coefficient and x velocity, we could see the phenomenon around winds. However, to understand the structure of the vortex, we have to move the cross-section a little bit. With the new slice of cross-section, which moved to minus 0.41 meters from the central line, we could see the detailed structure of the vortex. This is more clear. The simulation of the closed wind cat model appears highly magnitude of vorticity with a long tail flow. In this video, we can look closer at AWK to compare the difference in vorticity magnitude between the upper wind and the lower wind. If we switch the contour to the vorticity of the y direction, we could even see the vortices rotating in opposite directions. This is very interesting. The repeating patterns of swirling vortices arising in the wake of flow around AWK. It's quite similar to the von Karman vortex street phenomenon. With the LES turbulence model, we could even see the swirling vortices in both positive and negative vorticity. The legend on the left-hand side, the upper one, the streamline shows the vorticity magnitude, while the airflow across the AWK. The lower one is vorticity in the x direction with 4 cross-sections. We could see the relation between the airflow and the vortex. If we combine both isosurface of the Q criterion and the vorticity in the x direction, this is more clear. The vortex with positive value rotates along in anti-clockwise motion, and the vortex with negative value rotates along in a clockwise motion. In this video, you can see the detail of the vortex structures. Conclusions. The table shows overall study and the results. The results of benchmark validation using Java Foil are going well and prove the usability of OpenFOAM. The y+ value for the RANS model less than 5 and the LES model less than 1 is the key factor of accuracy in each simulation. The highest absolute value of the lift-to-drag ratio 0.36 occurs at the angle of attack of minus 41 degrees in parallel winds using NACA 4412 airfoil. The configuration of Case 5 comply the technical regulations of FIM and contribute to the racing superiority. Here is the bibliography. With all the remarkable research, we could contribute to the safety of racing motorbikes driving. That's everything for today. Thank you for your attention.